Good morning, everybody. Again, I know that we've been having discussion already, and the 8 o'clock just hit, so we're starting the recording right now. There were a couple of questions that we were discussing. The first one related to the exams and where they are located. The exams and every other assignment is on Canvas, okay? With the exception of the homework. Homework is actually on Pearson, what is that? Mastering Physics, okay? So that answers that question. The second question has to do with the discussion item for today. There is no discussion item for today because we already have one from chapter 17 that we had on Tuesday. Okay. However, okay, and this is a big deal, okay? There will be problems usually on Thursday where we go and solve them. You are strongly encouraged. You're not going to be graded on it. You're not going to be monitored on it, but you have to do it. I mean, this is not an option. You have to do it. You have to follow the steps in the calculations and redo them on your own. I'll tell you what the problems are. I will solve the problems. We'll go through them step by step. And we may at some point say, okay, you know what, these numbers, you're going to plug in the numbers and fix them yourself, okay? So which means that there is still some pending work that you need to finish anyway. And so we're going to go through those problems and do them step by step. There are two things that will happen probably. One of them is that we may make a mistake, okay? And that is your job then to send me a message, to send everybody a message that we did that problem wrong, okay? And we have to fix it, okay? Because even though I solved the problem wrong, you are still accountable for it to do it right. So that is your responsibility, okay? So this is very important that we have to do the problem for this reason, okay? If the problem does not have a mistake, and I would try not to do mistakes, but if the problem does not have a mistake in it, you still have to do it because you would want to basically reinforce that knowledge and know exactly what these problems are asking for, because you're going to be accountable for these problems come test time. Similar problems, similar questions, similar stuff, similar method will be applied to other problems in the exam. And if you built enough confidence in how to solve these problems during the exercises, basically, that we do together, you should not have difficulty with the exams when it comes time to it. So this is for you to do every time we meet on when we're doing applications, basically, from toward the end. Today problems are going to be problem 37 from chapter 17 on page 500, problem 113 from page 577, okay? The second problem 113 is a problem that you might have seen it also in physics 2, because heat conduction and current conduction are similar in a sense. There is some sort of an Ohm's law also in here obeyed, okay? So that is why it's interesting problem, because it involves calculus actually, which is one of the requirements for this class. Problem 37 is a typical problem involving calorimetry, okay? So that is something that you might see something along it in an exam. Granted, when you see it in an exam, problem 37, we're going to discuss it further. You might have additional questions in addition to finding something in it, okay? So those are the two questions. The first question related to the exams and where they're located, and the second one related to the discussion items. As I was saying before the recording also, some of you did not submit the discussion items. You still have time. You still have to the 29th, but it is a good recommended practice to submit your assignment as soon as possible, because assignments start to build up. And then once they build up, you start to prioritize things, and it becomes an issue if you don't submit some of them. So it's a good idea to submit yours. For those who submitted their assignment, I already graded theirs, and I already made comments when needed. And hopefully the rest of you also will take care of this, okay? For some reason, okay, good. So anyway, this session is also going to be recorded, and it's going to be posted immediately under the second one, and the first one, I'm sorry. And hopefully you will come back to it. It's going to be I mean, I know we have allocated for this one a long time, but we may not go through the entire period of 4 hours and a half or something like that. The reason why I'm saying that is because we're going to introduce the lab. We're going to do a break, first of all, okay? Because actually, even if we are on campus, we have to do the break because they're held in 2 different rooms, actually, the lecture and the lab. So we're going to have a break, then I'm going to explain the lab as we go about it, and then you can continue working on the lab on your own. I can leave the canvas open for you guys, and if you have any question, you raise it, and then when it's over, it's over. Okay, once we finish this, you will see exactly what I'm talking about. Sounds good?
Yep, sounds good.
Okay, very good. So let me finish what we started last time, namely chapter 17, and share. I want to share the screen. I want to share just the. Okay, so last time, basically, we introduced the 0th law of thermodynamics that enabled us to invent the thermometer. So we have a way of talking about temperature. And then we identified at least 2 commonly used systems of measuring temperature, namely the Celsius and also the Fahrenheit. And also introduced immediately the Kelvin scale, which is an important scale because that's what physicists use. And that is the one that for most of the time we're going to be using. Then we went a step beyond that, and we actually identified this expression in here that you have seen it in chemistry, the heat added to raise the temperature by an amount delta T for any material is proportional to the mass of the material, how much material you have, and then the type of material, okay? So this tells me what type of material you have. So this expression is called the specific heat in here in general, specific heat of that material. Each material has 1. Then we define the calorie in such way for the water, 1 calorie is equal to 1 gram of water that times 1 basically a calorie per degree Celsius per gram of matter. So if I take 1 gram of water, I define that of water to be the unit of measurements in here. So this is 1 times 1 degree Celsius going from 14.5 to 15.5. If everything is worked correctly, everything cancels and we have 1 calorie. So this is really the definition of the calorie, using the water as our beacon, okay? So at that point, this is as if a new unit of heat that we have in here. Immediately, before I go any further, Mr. Joule did an experiment. And in his famous experiment, basically what he did was he took an amount of water, doesn't matter how much, and he had a piston in here, and in the piston, he had he had this like ones that are used to for the summer, those things that sorry, fans, yes, very good, thank you. And he put several of them in here, okay? As this spins, of course, it does not extend all the way, okay? As this spins, these fans rotate, and as they rotate, they agitate the water, and as the water is agitated enough, it's you have a thermometer in here. So now we know what the thermometer does. It's going to measure this temperature for me. It doesn't matter, okay? And then on in here, you have gears in here to go through a pulley, and on the pulley, you have a mass in here. So you have a big mass M, and you have the water M, the mass of the water M, and you let this drop for a certain height, H. Well, in this case, I know what the energy is when this mass drops for this height. The energy in this case is going to be mgh. This you have seen it in physics 1. That's the potential energy, okay? It's going to be converted to a kinetic energy for this rotation of this rod, and this rod, that kinetic energy, if the energy is conserved, is going to be in a form of heat that will raise the temperature according to this scale. So if the temperature rises and thermometer detects the temperature, I would be able to measure how much heat was added. All I have to do is, since I know what the amount of matter is here, the amount of water is here, I know the specific heat of the water is exactly 1 because I took water in purpose. All I have to do is measure this delta T. So there are 2 ways for me to measure this energy. If I equate according to the conservation of energy, this is big M, I'm sorry, big M, this is this mass, okay? mgh, then I can measure what H is. I know what G is. I know what the mass that I dropped is. I can measure delta T using the thermometer. I have this C to be 1 by definition since I used the water. Then I have also what this mass of the water is. I have everything. So what this does for me is it's going to tell me how many calories are in joules or vice versa. It turns out this experiment gave us the following expression. 1 calorie, lowercase c, is exactly 4.18 or 4.19 joules. You can measure everything from one side one way and the other side one way, but what you did actually, you can, you have 2 ways of measuring Q. You have one way of measuring it in terms of joules, and now you know by definition how you measure it in calories, so you can equate the 2. There is another expression in here that I can use. 1 big calorie is 4,190 joules. Remember the big C and the little c. So this experiment, by the way, at that time they were not called joules. They had the energy of the so you can always measure it as kilogram meters squared per second squared. It was later on when Mr. Joule did this experiment that in his honor, the unit of energy was was named joules. So it's not like he went and said, okay, everybody, I did this experiment, so let's name it after me. It's not considered good taste to do that. So it was kilogram meter per second, meter squared second squared. That is the unit of energy. And then that conversion showed us, it showed 2 things. It showed that heat is actually energy. Not only that, but it gave us prescription of how to convert the 2. Does this make sense, this experiment?
Yeah, it does.
Okay, very good. So let's talk a little bit about that C now. So Q again is equal to mc delta T. So delta C now, we said it's 1 calorie per gram per degree Celsius, or equivalently, it's 4.19 joules per gram per Kelvin. It's the same thing, or degree Celsius if you like, okay? Because delta T doesn't care which scale you use to. Delta T is the same in degree Celsius and it's the same in Kelvin, because the difference between them is 273 shifted. So the difference stays the same. The difference between 20 degrees Celsius and 10 degrees Celsius is 10 degrees Celsius, or 10 Kelvin. It's the same scale. However, in Fahrenheit, it matters because of that factor of 5/9 or 1.8. Okay, so you have to be careful in here. So in this case, so this is the C, or equivalently, if you're using the kilogram, 1 big calorie per kilogram per degree Celsius is the same thing as 4,190 joules per kilogram per Kelvin. It's the same thing, okay? So from now on, the specific heat of water is 4,190 because we use the kilogram in the MKSA system. In the metric system, where is my mouse? We have MKSA, meters, kilogram, seconds, and amperes. Because the kilogram, so we're going to be using this number from now on unless the problem is differently or the lab asks for something different. But at least we have now a good value for it. So this is the whole thing has to do with this expression that you sometimes have seen in chemistry. I know that it should have been the other way around. You should have seen it first in physics and then saw its applications in chemistry. but I'm taking advantage of that, of the fact that you have seen it in chemistry to build on it. There is another expression that I'm not going to dwell a lot on it right now, but we're going to come to it basically later on with vengeance, honestly, namely Q. Remember, the mass of any substance is equal to the molar mass. This is the molar mass, if you like, times the number of Avogadro, the number of moles, where the molar mass is the mass of an Avogadro number of that substance. So if I use it this way, this definition becomes Nm, the molar, times the C times delta T. So this is just the mass of any substance, which is the number of moles times the molar mass. For hydrogen, for example, the molar mass is for hydrogen gas, that is H2, is 2 grams per mole, okay? And that means that if I have 1 mole, the molar mass is basically 2 grams, so it's going to be that much and so on and so forth. So this thing that you have seen it also in chemistry, where the number of Avogadro in here represents how many of that substance to have 1 mole of it. So again, this then becomes, by definition, because the molar mass and C are specific to that material, okay? So this is specific to that material, and here I have the number of moles N instead of the mass. So this becomes my C. This is a specific kind of specific heat called the molar specific heat. We're not going to be using this a lot now. Okay, we're going to come back later on because it depends on the process that the material goes through. If it is at constant pressure, there is something called the molar specific heat at constant pressure, CP. And if the gas goes through, or the system goes through a process where the volume does not change, then we're going to define the molar specific heat at constant volume. So there will be distinction in there, depending on the material. And there will be a nice relationship involving the two. So at this point, we're going to delay this discussion until chapter 19, where we're going to come back to this molar specific heat and try to find the 2 kinds that we're going to be needing for that class. So this expression, we're going to come back to it. We're going to be using this one still, MC delta T. We're not going to use the NC delta T unless specifically a problem tells you about it. Then in this case, you're going to use this one, okay? So this whole thing, as I said before, with no phase transformation. Meaning, if I start with a gas, I'm still with a gas, If I started with a solid, the system remains solid. If I started with a liquid, the system remains in a liquid, provided I can define what C is. For example, for the water, the C for the water vapor is not necessarily the C for the water when it's liquid, is not the same C for the ice. They are different values. This is the one that is equal to 1 calorie. It's the water in liquid form is the one that we define. So when water is in ice is not 1 calorie per gram per Kelvin. It's not the same thing also when it's also evaporated. It's not. So you have to be careful with that. When a system goes through phase transformation, though, we have a different thing, phase transformation. When a system goes through that, if the system, let's say, for example, take the water at 100 degrees Celsius, okay? If I have a certain mass of water, when it starts to evaporate, it's going to continue to evaporate until all of the mass is converted into gas. So the Q now needed to evaporate this liquid is going to be M, the amount of matter. Of course, depending on how much mass we have, the more mass we have, the more heat we have to add to it to convert it to gas. And the same thing, if I want to melt it, and if it was ice, depending on how much ice I start with. If I have a small amount of ice, then it requires just a little bit of heat to convert it to liquid. But if I have a lot of ice, obviously I need a lot of heat to convert it to water. So to liquid, I'm sorry. So in this case, it's always the amount of mass times a property, which is in this case, the latent heat. So again, this depends on the material. For example, the latent heat of evaporation for water is 2,200 and what is it? I probably have to refer to the table because I don't memorize these things, and I don't expect you that you memorize these things too. Okay. You find where the table is. Okay, the table 17.4 from page 557. I'm using the 15th edition, by the way. I know that in the 2019, when I was sitting in the what is that? The STEM Center, they had the 14th edition there, but we're not using the 14th edition anymore. So I don't know what the page is on the 14th edition. So on that one, it has the heat of fusion, LF, which is the melting point, if you wish. And then you also have LV for the vaporization, okay? So for example, for water, because we will need this a lot, it's 334 times 10. So for the water, LF, this is at 0 degrees Celsius, okay? It's going to be 334 times 10 to the power 3 joules per kilogram, okay? Because we're using the kilogram. If we're using the grams, it's going to be 334 joules per gram. LV, this is at 100 degrees Celsius, okay? For the water, it's going to be 2,256 times 10 to the power 3, again, joules per Kelvin, joules per kilogram, I'm sorry, okay? So these are the two values that you need to remember. It's 2,256, I know that, but per gram, okay? And the same thing in here, 334 per gram. You have to multiply by 1,000 to get the kilogram. So those are the latent heats for the conversions. For as long as you have this still amount of mass, there is no heat that is going to increase the temperature. All it does is it changes its form from one state to another state, okay, called phases. So that is basically, in a nutshell, how these processes are. I think we're ready to do problem 337. I know we still have a couple of other items that we're going to be talking about, namely the heat transfer, which is an important part of this one. And then we're going to come back to it. Excuse me. So problem 37. Problem 37 is on page 572. At this point, I would strongly urge you that you're going to follow the steps and do them again, okay, with yourself. So it says a blacksmith cools 1.2 kilogram chunk of iron. So the mass of iron is, let's put it in here, Fe for iron, 1.20 kilogram. The reason why they put the 0 there is because of the sig figs that you guys have had from way back in physics 1, okay? Although I'm not going to be doing a lot of basically stuff and talking about the sig figs in this class and things like that, but keep that in mind, okay? If you find an answer more precise than what you started with, it doesn't mean much, okay? So you have to be careful with it. So was initially at 650 degrees point C. So this is T1 was 650 degrees Celsius. Okay, again, you have 4 sig figs in it. By trickling 15 degrees water over it. So this is the temperature of the water that we started with, okay? So this one, so this is for the iron, and this is for the water. We started at 15 degrees, so we pour it on it. You take it from there. 15 degrees is a cool water, by the way. Normal temperature of water is more than 20 degrees. So you take it and you start to trickle on it, little by little, okay? 650 degrees is a very high temperature, by the way. It does not probably radiate in the red region already, but it's really very hot. I mean, 650 degrees is a tremendous amount of temperature, okay? It's above the melting point for lead, but the melting point for iron is still very high. So imagine yourself, you have a block of 1.2 kilogram of iron. The density for iron is almost 8 tons per cubic meter. Cubic meter is this much. Where is my other hand? Moved. No, it's actually the other one. Okay, so it's this much, probably 1 meter. So think about it this way. That's a cubic meter. It is a good idea when solving problems, when discussing physics, to have a visual. 1.2 kilogram, what does that mean to you? So the density of water, if I take this much, basically, that is 8 tons, but I'm not having 8 tons. I have 1.2 kilogram. That is 1,000 divided by another 8 or 7 or something. So it's a very small quantity. So probably it's this much of iron, okay? Maybe this much, okay? That is going to be 1.2 kilogram because of the high density of iron. It's very dense, okay? So that is something to keep in mind when you're talking in material. So if you're going to do this experiment at home or in the lab, you have to think of how much iron are we talking about? This much. You warm it up to 650 degrees, and now you start trickling on it little by little, 15 degrees Celsius water that you take from the refrigerator, and you start, and you have thermometer there that is telling you that it's coming at 15 degrees Celsius. But the water boils, okay? So the water, when it touches the surface, its temperature rises from 15 degrees Celsius to 100 degrees Celsius, in which case it's going to evaporate. So the water temperature, when it touches the surface, is going to go through 2 processes. One, if you wish, its temperature is going to rise. So this is the mass of the water times the specific of water, delta T, where this delta T is from 15 to 100. Well, this delta T is 85 degrees. Plus another process where it evaporates this, where this is the LV. So this is how much heat is needed to do that. So each droplet of water for the entire mass is going to go through this process. So if you bring this much mass, part of it is going to raise its temperature by 85 degrees to bring it to a boiling point, and then it's going to even evaporate it. Okay? All of the water boils away. So there is no leftover of water. Everything boils away. Okay? And the iron ends up, so the T final of the iron is going to be 120.0 degrees Celsius. Okay? So that's how much the temperature. So basically you cooled it down from 650 to 120. Imagine yourself trying to build a sword or something. That's the blacksmith's job, trying to do these things. Okay? How much did the blacksmith use? Okay, I need the C for iron. C for iron is needed because iron, I have a mass which is 1.2 kilogram times the C of iron times the final temperature, which is this 122, minus T1 of iron, which is 650. This is the heat extracted from iron. Again, I'm going to look back into page that I mentioned for the table. on page 557 and look at the iron in there. Actually, I made a mistake. That's not the same table. We need the one for the specific heat. That's the one for the melting points. We need page 17.3. I'm in table 17.3. Okay, 17.3. That's the table that we will need now. That is the one that has the C's in it. And that is on page 555. Okay. And that should tell me iron is actually in the middle of the page. The specific heat is 470 joules per kilogram per Kelvin. So C for iron is 470 joules per kilogram per Kelvin. Okay. So at this point, we have the mass of the iron, we have the C of the iron. Okay. And we have the difference in temperatures, because all we have to do is subtract 650 from 120, that's correct. And then we have this delta T, which is 85 degrees or 85 Kelvin, it's the same thing. And then we have this C, which is 4,190 kilogram per degree per Kelvin per kilogram. What is it? Joules per kilogram. And what else are we missing? LV, we have 2,256 times 10 to the power 3. Okay. The only thing we don't, because of conservation of energy. Because where are we getting the heat from for the water to evaporate it? We're getting it from the iron. Does this make sense so far?
Yes.
Okay, very good. Thank you, Maggie. So all I have to do is equate the two things. And if I am careful enough with the signs, everything will work out itself, okay? So what I'm going to say in here is that the mass of the water times the specific heat of the water times the delta T, which is 85 Kelvin, if you like, it's the same thing, plus the mass of the water times the latent heat of evaporation for the water must be equal to the heat that we removed from the iron times the specific heat for the iron times the difference between 650 and 120 is what? 530 Kelvin. This formula should give me MW. I already took care of the signs, so because what I'm saying in here is that the extracted heat from the iron went to do this thing in here, because we are not assuming that heat is lost to the environment or anything else. Does everybody agree with this analysis, this argument?
Where did the MW and LV come from?
LV is coming from the table, the latent heat of evaporation from for water. That's table 17.4. Okay, so what this is saying in here is that, look, you have taken this much iron, and when you drop on it the water, part of that water, the temperature of it, it's sitting at 15 degrees Celsius, okay? Its temperature will rise to 100 degrees Celsius. Not only that, but it's going to evaporate now. So for it to go from 15 degrees Celsius to 100 degrees Celsius, it needs heat. This is how much heat it needs to do that. And to evaporate that entire mass of MW, you need to multiply it by LV to find how much heat is needed to evaporate that much water. That is the heat that was extracted to lower the temperature of this piece of iron from 650. It started at 650 down to 120, because it needs to lose heat in order to go down from 650 down to 120. And that is given by the mass of the iron times the C of the iron times the change in temperature, 650 minus 120, which is 530. Okay, but this have to be careful in here. This is for iron, and this is for water. Make sense now?
So Dr. Busidi, just to be sure, so when we're doing the delta T for the iron though, why would it be 650 minus 120 and not the other way around, 120 minus 650? Because T2 in this case is the 120, correct?
Yeah, T2 is the 120, but what I'm saying in here is I'm taking it in absolute value in here. The reason why I'm saying it's an absolute value, technically, this is what's going to happen, okay? What I'm saying in here is that the heat extracted from the iron is the heat added to the water. So technically, the entire heat that we have in the process is Q1 from the water plus Q from the iron must be equal to 0, because before we did that, there is no heat added or subtracted, okay?
Right.
So we had no heat. So part of it is going to here and the other one. So from this expression, I can write that QW is equal to minus QFE. If I do that, then do what you said. Then in this case, this is a positive value because the water went from no heat up to temperature 1 to 100 degrees plus evaporation. So I need to add this value in here. So this must be a positive value. Has to be a negative value because of the fact that the temperature was 650 down to 120. We extracted from it. So the minus will take care of that. So this is minus M iron times C iron times then 120 minus 650. Okay. So the minus and the minus will take care of themselves.
Okay.
Either argument is saying the following: the heat you extract from the iron, this is the heat extracted from the iron, goes to heat up the water and then evaporate it. Two processes in the same time. Okay.
That makes sense.
Okay, so that is really the key argument. There is no third party involved. There is nothing else involved. If we had aluminum sitting in between them, or if we have a container where we do this, the container might play a role because the container's temperature might change. And if that's the case, then I have to take that into account. Then this equality will not be correct. Okay?
Okay.
So you have to be careful. If we have the air in the room, also the air might warm up or the air might cool down, depending, okay? Depending on the process. So in that case, I have to be careful also. If we do this entire experiment in the refrigerator, for example, it might affect the piece of iron from 650, it might bring it down lower to begin with, okay? So the air could be could play a role, but because we have isolated this two from the universe, so one heat has to go to the other one. There is no other way. So in this case, the heat that was added to the water sitting at 15, it was minding its own business at 15 degrees Celsius. Then somehow the temperature went to 100 degrees and still water, then evaporated. Where is that heat coming from? It has to come from the lost heat from the iron. And this is the lost heat from the iron. Okay? Makes sense to everybody else also?
Yeah.
Okay, very good. How about some other people in the class?
Makes sense.
Yeah.
Okay, very good, very good. So as long as I have everybody on board, please make sure that you understand things because they are important for us, okay? Let me take you to the next step in this process, really, which is really the lab, Okay, how much time we still have? To understand what calorimetry is, and then we're going to go to the heat of the conduction, which is important in this class too. Okay, and that is going to be the second example is on heat example, second problem, which is on heat conduction. Okay. Imagine with me, this is the lab, okay? This is basically what the ideas of lab are. Imagine with me the following process. We have iron or aluminum or tungsten or whatever material that you have, and sitting at temperature T1, okay? And you have an amount of mass that is M1, okay? And it has its own specific heat that is C1. And you don't know what C1 is. You would want to know what the specific heat for iron is, what the specific heat for aluminum is, what the specific heat for copper is. So you would want to understand this. You would want to find a value. The only thing you're allowed to do in this case is to find that of water. Once you have defined that of water, that's it. Then you have no room to wiggle. You have to find what the others are. So it's sitting at temperature T1. Let's say, for example, it's very high temperature. Let's say 120 degrees or 170 degrees, depending. And you put it in a container. Oh, by the way, I didn't do the math in here. I'm expecting that you guys find this MW. I mean, I'm supposing that you guys are going to finish this. MW is equal to M iron, which is 1.2 kilogram, times the specific heat for iron, which is 470, was it? Iron is 470. Everything is going to be in times 530, divided by C for water. C for water is 4,190 times 85 Kelvin, plus LV for water, which is 2,256 times 10 to the power 3. So you're supposed to do the number. Does anybody have a number in here? Because I want to understand what this number. Does anybody have a calculation what these numbers are? So we have 1.2 times 470 times 530, and it's going to be in kilogram, by the way, the mass of the water, divided by 4,190 times 85 plus 2,256, 10 to the power 3. Or should I put a calculator in here? Was anybody able to get this number for us?
I'm solving it right now.
Okay, so let's do it together. Everybody really have to play their role in here. Cannot rely on us to do this thing. Everybody has to do it. Does everybody look the calculator in here that I have pulled up? Yes, no?
Yeah.
1.2 times 470 times 530 divided by open parentheses 4,190 times 85 plus 2,256 times 10 to the power 3.
I got the same.
Yep, I got 0.11.
Okay, 0.114, okay, because of the suffix. Does everybody get also the same thing in here as I did?
Yeah, I got 0.11.
Okay, very good. Okay, let me stop sharing. Let me share. So we got 0.114 kilogram. I have in here a 700 milliliter bottle of water that I bought from Virginia the other day when I was there. I don't know if this brand Deer Park exists in California or not. Okay, this is slightly less than a liter, okay? Because remember, the density for water is 1 kilogram per liter, and this is clearly not 1 kilogram. This is almost a tenth of a kilogram. slightly more than 1/10 of a kilogram. Okay, 0.11 is basically 10. So divide this into 10, it's probably about this much water. Okay, and yes, we started with 1.2 kilogram of iron. All we needed was 1/10 of a kilogram of water to do this whole process. We don't really need a lot of water to cool it down. Okay, and that speaks volumes about something else in here. The specific heat for iron is 470. This is the number that, where is it? 470. 470. Whereas the specific heat of water is 4,190. Water has a very high specific heat, relatively speaking. So if you have, for example, this is a known fact, and that is really plays a major role when it comes, for example, for the weather, because land cools a lot faster than the ocean. The ocean acts as a regulator for the weather, and also a piece of iron also has a lot less specific heat. For example, the spoon that is made out of aluminum has a lot less specific heat than that of water. So water has a very high specific heat, and this is why you didn't really need that much water to cool it to this temperature. Okay, so let's talk about this one then. Okay, so we have a material here, and we have an amount of water in here that is sitting at a given temperature. Let's say, for example, T water. Let's call it T0, okay? Just because we call this one T1. So this is for the water, and the specific heat for the water is known to be 1 calorie per kilogram per Kelvin, or I have to be careful in here. This has a delta T in it, okay? This one also has a delta T in it. So you cannot say that it has heat at a given point. Heat is not, with an emphasis on this, a state variable. What do I mean? You have had this discussion probably sometime when we did work and energy theorem, okay? The kinetic energy turned out to be a state variable, meaning you can define kinetic energy at a given point in space, 1/2 of mass times velocity squared, but you cannot define the work as being a state variable. The work is done over transition, going from point to point. So the work is not a state variable. The work, it depends on the path that you take. Same thing with the heat, is not a state variable. You cannot tell me that a substance has heat in it. It has temperature, but doesn't have heat. It can gain heat or lose heat when its temperature changes, but it does not have heat in it. Okay, so when you touch it, you have to say it has temperature. What you feel going on in your hand is heat transfer. If it was hot from the container to you, or if it was cold from you to the container, that's what you feel. Okay, but you can tell it was hot, it has high temperature, if heat is coming to you, if heat is actually leaving from your hand to the container. So it's very important that we have to have that distinction in here. I'm going to talk more about state variables down the road too. Okay, do you guys remember this discussion from physics 1? Yes, maybe.
I don't remember it at all.
Yeah.
Okay, no problem. Don't worry about it. Yeah, we're going to come to it. Okay, so what we do in this case is we bring the two substances together. So T1 is not the same as T0. So we take this mass in here and put it in here, and we wait for thermal equilibrium. What happened in this case, the two substances will reach the same temperature, T2. T2 is clearly going to be more than T0 and less than T1 if T1 is more than T0, meaning they reach somewhere middle ground. So here is how the experiment would look like from the vantage point of temperature. So this is time, and this is temperature. T0 starts low and then starts to increase and reaches a certain point. It's not going to change. T1, so this is T0. T1 starts high and then come down, and they both will reach the same limit in here. So this is what I meant by T2. Okay, so the two substances will reach a certain temperature, which is their common temperature in this case. Clearly, the first substance in here sitting at T1 lost an amount of heat that is equal to M1 C1 times T2 minus T1, or an absolute value if you like, because this one is clearly greater than that one, it's T2. So this is T1 minus T2. So this is an absolute value, meaning how much heat lost. It's the same question that Amr asked earlier, okay, basically, okay? The same thing, the second substance in here, so I'm taking it in absolute value now, gained heat to be equal to M1, I'm sorry, M2, did I call that the water in this case? MW, yes. MW, because I'm going to be using water, CW times the final temperature, which is clearly higher, T2 minus T naught. Okay. If I can measure T1, if I can measure T2, if I can measure T naught, if I can measure M1, if I can measure MW, and if I know what CW is, this will allow me to find C1. Because all of these quantities are measurable. Thermometers will measure these temperatures. And this one is by definition given. Scale will give you these masses. And the only thing that is unknown from this expression is the specific heat. That is in a nutshell what you have to do. The only thing you have to be careful with when you do the experiment is what units are you going to be using. That's all. If you're using calories, if you're using grams, if you're using degrees Celsius, stick to that convention, okay? And that's it. And you're going to find C in terms of those units and then compare it to the table. Table from page 555, 17.3. Okay, because that's basically what we're doing. So this is calorimetry in a nutshell. You have two substances, one with a known specific heat, which is really the standard, which is in this case iron, water, and then you the other substance you can find what its specific heat is. That's it. Okay, so this is in a nutshell what this whole experiment is. Make sense?
Yeah, it makes sense to me.
Yep.
Very good. I mean, somebody might argue, and again, Amr probably will have the same question again, and he's entirely allowed to it, is how in the world we get that sign minus in here? And again, the argument is you can, since these two systems are isolated from the rest of the universe, I can say Q for the substance plus Q for the water must be equal to 0 because there is nobody adding or subtracting heat from them. We're not doing this experiment in the air or in the refrigerator or anything like that. So Q for the water must be equal to minus Q for the substance, and the minus will take care of everything else when we flip the sides. Otherwise, take it in absolute values. It's the same thing, okay? And the bottom line is temperatures in degrees Celsius, yes, they can be negative and positive, but in Kelvin, they can never be negative. There is nothing lower than 0 Kelvin. As a matter of fact, 0 Kelvin is an idealization. You cannot even reach 0 Kelvin, let alone negative Kelvin, okay? The masses must be positive all the time. Specific heats are always positive no matter what, okay? So this you have to be careful with when you're doing experiments. So you cannot find a specific heat that is negative. It's always positive, okay? So I think that closes the book on these ideas. And we're going to come back to them. Let me get into the last part of this chapter. Still have a few time. And that is heat transfer. We're going to do heat transfer in about 20 minutes. I used to teach heat transfer for engineering classes for an entire semester, okay? So we'll try to squeeze it in 20 minutes. Anyway, there are 3 processes for heat transfer. There is convection, which typically we don't start with it. We start with conduction. This is the #1 process that is easy to understand. The second one, which is actually the hardest of them mathematically, but it's actually easy to understand too. And the third process is radiation. So these are the 3 ways that heat can be transferred from one point to the other, okay? Conduction, basically you have 2 substances typically at different temperatures, and you make them in contact using the third material. So there is a solid contact between the two substances, and the heat is transferred from one side to the other side in a similar fashion like currents does. As a matter of fact, electrons are the same culprits in this case, okay? A good electrical conductor like iron, for example, or copper or silver are good heat conductors too, okay? So this is one thing. So this requires a medium. Convection requires usually a fluid of some sort. And this is the dynamics of fluid themselves. So you have a fluid that is sitting at a high temperature, T hot, and in here, T cold. Because of the fact that the higher temperature, the colder temperature is denser than the higher temperature, so the denser will fall. And as it falls, it expands, and its density is less. As its density is less, it rises. Once it rises, it's going to cool down, taking with it the heat and transferring it from point to point. So this process looks like this, actually. And this is exactly what happened in the boiling, for example, of your soup. When you put it under the furnace, when you put it on the stove, the bottom, it's immediate contact with the heat source, and the top is in contact with the air. So the air is cooler than the stove. So in this case, that part gets hotter and its density is less, so it rises. The top part is cooler, so its density is less. The density is higher, so it's going to fall. And you have that circular motion. You see it in the bubbles that form. Okay, this process is actually a very dominant process in the weather phenomena. That's how masses of air move from point to point in the atmosphere, whether on Earth, whether on Jupiter, whether on, what is that planet? Venus, all of the planets that have gas in them, they have this one. The sun actually is dominated by this process. There is a whole layer in the sun that is actually a convection zone. So you have the core of the sun, then you have the radiation zone, and then after that, there is a convection zone where the masses of mainly hydrogen and helium do that to transfer the heat from the lower radiation zone to the photosphere, the upper layer of the sun that we see, okay? So this is actually a process that is known for most of the stars. Some stars like the red, no, not the red, the dwarf, what do you call it? Dwarf stars, brown dwarfs, they don't have that. They have the, if I say it backwards, I think I said it backwards. These giant stars that don't have the convection zone, okay? They have all of the radiation zone. Anyway, the point being in here, this is a process that is dominant in transferring heat from point to point, okay? And the physics for it, because it involves dynamics of fluids, is a little bit complicated. We're not going to get into it that much. So let's talk about the one that is of interest to us, namely the conduction zone. And then we're going to talk about the radiation, okay? For the conduction, basically, dq over dt, which is by definition the heat current. To measure the heat current, the units for it are the same units for heat, which is joules divided by second. And this is, if you guys know, this is watts, that's all. This is a power, some sort of a power, okay? So this, for this material, is going to depend, first of all, on the material. This is the heat conductivity for the material. The greater the area, I mean, if you have a big window, it's going to conduct more heat than a small, narrow window. So that's basically have to be careful with it. So depending on the area, the longer the depth, the longer the depth of the insulator, the less heat is transferred. If you have a thick wall versus a thin wall, the thick wall would be more insulating than the thin wall. Makes sense, doesn't it? So it's inversely proportional to the length. So the longer it is, the less heat is transferred. The thinner it is, the more heat is transferred. The wider the region, the more heat is transferred. The narrower, the less heat is transferred. So it's called plus also the gradient of temperature, delta T. Let me write this expression again. H, which is the heat current, is proportional. This is the heat conductivity of the material. If you have a piece of iron, for example, trying to use it to insulate two regions, versus if you have a piece of wood, for example, trying to use it to insulate two regions, the wood is more insulating than the iron. So this is a property of the material that you're trying to use. The area, so if you have very big area, it's going to conduct more than if you have a narrow area. And the longer, the thicker it is, the less heat is conducted. The thinner it is, the more heat is going to go through. Times, of course, the gradient of temperature. If the outside temperature is 110 degrees Fahrenheit and the inside room is 60 degrees Fahrenheit, the AC has to work very hard to maintain that gradient of temperatures. If the outside is, let's say, for example, 87 and the inside is 85, then the AC does not really have to work that hard to maintain that gradient of temperature. So the gradient of temperature plays a role too. Does this expression make sense to you guys?
Yes.
Yeah.
Yes.
Very good. So this is the expression that we use for this K depends on the material. Again, this K, you're going to find it as a table, and it's actually given on page 561, table 17.5. So that gives me the Ks for different materials, okay? So as an example, aluminum is 205 watts per meter per Kelvin, because you have in here meter squared, and you have in here a meter. So the meter squared and the meter cancel, and you have in here Kelvin. So, and this is in watts, as I was saying before. So the units in here is watts for K divided by this meter divided by this Kelvin. So the units are correct, okay? So for aluminum, and if you look at brick, for example, is about 0.15, and fiberglass 0.04. So the higher the value of K, the more heat is going to be lost. So if we're going to go to Walmart, not Walmart, if you're going to go to Home Depot, for example, and get yourself good insulating material because you don't want heat to be lost, then in this case, you better look at this table and find exactly what type of material you're going to get. Looks like fiberglass and cork and all of these materials have very low, styrofoam actually has very low also conductivity, 0.027. So that's what you use for your coffee. You don't want the heat from the coffee to come to your hand. So again, this table is a useful table. Please look at it because it's going to help us do a lot of these problems also, okay? So this is expression, excuse me. The last one that we're going to do in here is for the radiation. The radiation, we're going to come back also to the radiation way down the road, trying to understand it, okay? I think chapter 38 or 39, I don't remember exactly when we're going to come back to it, but it's really around those times. So for radiation, and this you have seen it actually in chapter 32 or something, when you solve for Maxwell's equations, that materials emit EM radiation, and that's exactly what this is, electromagnetic radiation. So it depends on the surface, A. The more surface you have, the more radiant it has. It depends also on the temperature to the power 4. It depends also on the constant, is it sigma or is it alpha? It's sigma, okay? And it depends on the emissivity of the material. So this is H also. So the fact that the sun is sitting at 5,500 Kelvin, you can take that to the power 4 times sigma. Sigma is a constant. Again, at this point, let's just call it as such, which is 5.6 times 10 to the negative 8. This is a constant. We don't know where this constant is coming from, but down the road, we will have an explanation for where this constant is coming from, okay? Times the area, obviously, the radius of the sun is 770,000 kilometers, so 770 million meters to the power 2 times 4 pi, give me the surface area of the sun. So this is 4 pi r squared. For a spherical object, for you, for example, and I, we don't have spherical object, but we can find the surface area. And we're sitting at a temperature of about 300 Kelvin. You and I were sitting at 300 Kelvin. That's room temperature. That's, if you measure your temperature, probably slightly more than that, okay? But that's 36 degrees plus 273. So a human being has a temperature to body of 36 degrees plus 273. So 90309 Kelvin. Okay, so that's the number that you're going to be using for a human being. Times E. E is the coefficient of emission. That too, you have seen it in physics 2 when you did the solar sailing, and you talked about the solar radiation, and the solar radiation, it depends on the emissivity or the absorption of the material. Okay, for the sun, we take it E equals to 1. This number varies from 0 to 1, from perfectly absorbing material to a perfectly reflective material from 0 to 1. Okay. Typically, we take it 1 because it's a small number. So this is the coefficient of emission. It has another name that I don't want to say because I'm not sure of it. Coefficient of emission, because of the fact that in astronomy they use another name for it. Is I forgot the name for it right now, but it depends. Some planets, like for example, the moon, has a coefficient of emission 0.12, for example, for Europa, which is the brightest object in the solar system. In terms of coefficient of reflection is about 0.6. So this depends on the objects in we talk about. For the sun, we take it to be 1 because all of its radiation is basically emitted from the sun, and it reflects depending on the materials. For white clothes, for example, they have a very coefficient emission coefficient. For dark clothes, it's the opposite. That's why in the desert, it's a good idea to cover yourself, first of all, to minimize this area, A, of emission, and also with white clothing, if you can, because then in this case, the radiation as it hits you is going to be reflected immediately so that you don't get too warmed up inside. So this is an important technique that you have to learn to use if you're going to be wandering outside the desert, okay? Again, this formula in here has T to the power 4 in it, meaning that with a slight change in the radiation, an object can emit a lot of energy in this form of radiation. You have to understand one thing in here. In this form in here, this requires a fluid of some sort. This requires material. This can propagate even in vacuum. Case in point, we can see the stars, we can see the sun, and the distance between us and the sun is mainly vacuum. There is nothing between us and the sun. Okay, so radiation is a way for heat also to be transferred, and it can transfer through vast emptiness, basically, of space without and that's because of the electric field and the magnetic field. When you solve Maxwell's equations, you found that the electric field and the magnetic field will propagate in such a way that both of them are perpendicular to one another. If this is what the electric field, this was the magnetic field, and they propagate with the the pointing vector in this direction in such a way that they travel in vacuum. They don't really need the medium to travel through. And this is exactly what this expression is telling you, but it's telling you how much you're going to get from it. So for astronomy, this is an important expression, because if I can find the temperature of a star, I can find its intrinsic brightness. And if I can look at it and see how bright it is, I can determine how far it is. There is another expression, but I'm not sure if it's in here or not, and that involves the expression. I'll find it for sure. Because we're going to come back to the black body radiation, because this is part of the so-called black body radiation.
Professor, what does H stand for?
Okay, we're gonna come back to it for the black body radiation because, sorry?
What does H stand for?
H stands for the rate at which heat is transferred, dq over dt. The heat current.
Okay,
Okay. So this is in watts because Q is in joules. Joules over second is watts. Okay. So that means every second, this much energy is being basically leaving the body. And there is a discussion about a net emitter and net absorber, depending on that coefficient of E, depending on how much heat goes in. If you're sitting outside in temperature, let's say, for example, I don't know, let's talk Celsius, okay, 40 degrees and your body is 36 degrees. So there is actually an equation here that has to be balanced because you're taking some to be also taken into account. And the difference t to the power 4 minus the other t to the power 4. That's really how this expression is going to be looked at. Okay, it's 9:12 right now. The other law, so this is called the Stefan-Boltzmann law. There is another expression that is the Wien displacement expression, and that relates the wavelength to the temperature. But because we're not talking about wavelength in this thing and here at this point, we're going to defer that discussion later on when we get into the black body radiation, because that's going to give us an explanation for where this expression came from, number one. Number two, when people try to explain it with the old physics, basically, that of Newton, this led to an immediate catastrophe known as the ultraviolet catastrophe, UV catastrophe. So at that point, we knew that there is something the matter with the old physics because of the fact that this is an accurate law. Okay, so we know that there is something the matter with that. So we had to fix the old mechanics, introducing quantum mechanics. As a matter of fact, Mr. Planck, when he introduced that fixing, he was not even himself convinced of it. So he was kind of apologizing for it. And later on, he won Nobel Prize for it. So to show you what happened. Okay, I'm going to take a break for about 15, 20 minutes. Maybe we will meet at around 9:30.
Sounds good.
Sounds good.
Okay, so I'm going to leave this session open. I'm not going to close it. So you guys can go and grab something to drink or something. We'll back around 9. So we're going to do the example and then we're going to dive into the lab. Okay. See you in about 15 minutes. Okay. You don't have to. You don't have an audio if you have. Still have 1 minute before we resume the time. For those who are here right now, did you guys have a chance to look at the lab?
I had the chance to, take a look at the file. It looks like it's a fillable PDF from what I'm seeing, right?
Yes, it's a fillable, but there is a mistake. Formula 2 is wrong.
Okay.
Equation 2 is wrong. It should be A over L.
Hey DJ, in order to take the lab, we have to
Okay.
do the quiz first.
9:30. Yes, I think the first week you have to go through the sequence. Yes. Okay. I'm going to share with you today the lab to see how the lab look like. And you're going to see mainly that the things that we discussed earlier in the lecture are going to be explored in this lab. So you should be able to do it. But I think some of the items are in sequence or order, so you have to keep that in order. Okay. Okay, so let me see where we stopped. I know we said we meet back at 9:30. We still have probably one person who is not here yet, or two. But we're going to make this thing available later on. So where are my notes in here? Let me share the screen. So this is basically where we last talked about the conduction. As I was saying, for those who have had chance to go through the lab instructions, you will see that equation 2 is wrong because it has L over A should be A over L. The larger the area, the more heat is going to escape. It's not the other way around. The longer the region, the less heat is going to escape. So that's true. Denominator. So this one in here is correct. Use that formula. Okay, so let me make sure that we covered all the items this chapter. I think we did, okay, for the main part. Oh, we did not talk about the thermal expansion. So let's talk about the thermal expansion briefly, which you must have done something similar to it when you did elasticity a long time ago, except now it's due to heat, that's all. Okay. Okay. And you raise its temperature. When you do, it's like the entire body actually changes, but its length will change by an amount that is delta L. So this is L naught, the initial length, and this is delta L. So in this case, delta L is going to be equal to proportional to the temperature. The higher the temperature gradient, the more the length is going to extend. Okay. Times the initial length, of course, times the properties of the material. Alpha is a coefficient of linear expansion. That depends on the material. Okay, so that is basically how this. So I think we have a lab for that too. Coefficient of linear expansion. Not this lab, but the next one probably. So this is something that is noticed. So when, for example, you're trying to build rail tracks for the train, you have to make sure to leave a gap between them, because this, during the summer, they will expand. And if you don't leave a gap between them, they will buckle and the train could derail. So you have to be careful. Even on the freeway, the different slopes of the freeway, they put them, there is a gap between them. And that's what you hear when you're driving on the freeway. Those repetitive, sounds like as if you're going through a broken road. Because in the summer, again, the road expands, and they, if you don't allow for that, they will buckle. buckle also, there is a problem in there too. So that is something that is properties of a materials. If the temperature increases, the length changes. As a matter of fact, it's not just the length, it's actually the entire volume changes too. Okay, so delta V is given by, again, the initial volume times the gradient in temperature times the coefficient of the bulk expansion in here in this case. Okay, this is the volume expansion, and this is the linear expansion. For a material, like for example, a 3D object, there is a simple relationship between beta and alpha, and that is this one. This is very easy to prove. I mean, all you have to do is the volume is usually proportional to the cube of the length. I mean, if you have a volume, even if it's not a cube, L times A times B, each and every one of them will expand this one by delta L, this one by delta A, and this one by delta B. And if you do a Taylor series, the leading term in it is going to involve the product, or at least in the volume, is going to involve this product of these three quantities, okay? And I'm sorry, it's going to be L times delta A times B. Anyway, if you do a Taylor expansion, you're going to notice that in this case, delta V to the leading term in delta V is going to be equal to 3 in this case, times the L squared times delta L. And again, all you have to do is multiply by another L divided by another L, and this will become your V. And this is going to be your delta T, as it's defined from the other expression here, alpha delta T. Okay. So there is this simple relationship. If you are curious trying to see the properties for it, I would be more than happy to share all the details for it. Okay. But the point being in here is this alpha and beta are actually properties of the material. Different materials expand at different rates. So this is basically in a nutshell. And then you have the Young modulus, the expression how the Young modulus is related to alpha, and that is from elasticity from the previous chapters. We're not going to do much with these expressions, honestly. That's why I really don't emphasize on them. And that covers all the things that needs to be covered in terms of the theory for this class. We get into the example and then get into the lab, and that will be it, okay, for this chapter. So the example that I thought we should do is example 113 from page 577. There is something the matter with this problem, and I'm going to tell you what it is. And that's why it's a good idea to stop at this kind of problems. So the problem is 113 from page 577. When you're solving problems in physics, the first thing you have to do is read them. When I say read them, you really have to read them and think about what you're reading, okay? Try to visualize it, try to, excuse me, understand as much as possible from it. And then try to write what you can take from there and draw a graph. At the end, you're going to put everything you need to find, everything you know, and try to build as much as techniques that you have. That's where you learn all kinds of techniques to solving problems, from geometry, from calculus, from physics, from whatever you have in there, and put them together and find a solution. Once you find a solution, try to see if it makes sense to you. Criticize your solution, see if it makes sense. We already did that with the first problem. Already went through it, we read, we tried to understand, we even visualized how much mass we have, how much water we have, and at the end we found an answer, and we saw that it makes sense, okay? So that is basically how we're going to approach this one. So problem 113, and when you read this problem, you will discover what I'm talking about. It says a frustum, which is a shape basically, of a cone has a smaller radius R1 and larger radius R2, and length L is made of material with thermal conductivity K. So let's draw this shape in here. So basically we have this shape. You have a cone, or parts there is of a cone. This radius is given to be R1. And this radius is given to be R2. That's given. And the length from top to bottom, that is L. Okay. And the cone has a conductivity K, thermal conductivity K. Okay. Derive an expression for the conductive heat current through the first term when the side with radius R1 is kept at temperature TH. That's the problem. It says the side with radius R1 is kept at TH, but when you look at the picture, it says TC. So there is a contradiction in here, okay? And then it says, and the side with the radius R2 is kept at temperature TC. So this is TC. Whereas the picture, it says TH. So the question is, which one? The picture is correct or the verbiage is correct? Okay. So it doesn't matter. We're going to go with the verbiage for right now and see where it's going to take us. So if the verbiage is correct, then heat must be going this way. So this is a direction of the heat must be going from the hot region to the cold region. That's basically what this whole thing is. So it depends on where this thing, where TC is and when TH is. If both of them are equal to one another, there should not be any heat. I mean, if both of them are sitting at the same temperature, heat is not going to the top or coming to the bottom. It doesn't matter. So the two temperatures are the same. So at this point, I'm going with the verbiage. And I'm going to assume that R1 is hotter than R2. Excuse me. So that's why I brought this problem to your attention, because it has sometimes issues with the problems like this one, and you have to be critical when you see them. You have to basically do something about it yourself, okay? So if it turns out that the picture is more correct, then we should be able to fix that once we find a solution, okay? We should find H to be negative then, because heat was not flowing in that direction to begin with. So it says, hint, parameterize the axis of the first term using the coordinate X, using equation 1721. 1721 is the equation we just wrote, the last one for the heat conduction, okay? 1721 gives me H equal to Ka times delta T over L, okay? And through a differential slice of first term with length dx, area A equals to pi r squared, where r is a function of x, and temperature difference dt, separate variables and integrate dt on and dx. Okay, so basically they told us what to do. So what I'm going to do is I'm going to draw this one backward. Start with the TH, because then H is going to be positive. So this is the small version, this is the big one. So this is TH, this is TC, and then I'm going to take a slice of this shape. This is the X direction of with dx, situated at a position X from the axis. So this is going to be my origin of the y-axis. This is X equals to 0, and this X equals to L, the whole thing, okay? The temperature starts from TH and ends up at TC. So, and the H in this case is going to be the same. The amount of heat that is going to be escaping from one side to the other is always going to be the same amount, because this is a constant steady flow of heat, Okay, it's like current basically. If you have 1 ampere in here, it's 1 ampere in there. It's the 1 ampere being thrown through the entire thing. Except in here, you don't have ampere, you have watts. Okay. In other words, there is no accumulation of heat. Not all of a sudden it sits in here and stops. Like as if I have a sink of heat in here. Somehow it's draining the heat. I have 1 watt comes in here, and all of a sudden half a watt somehow continues. No, it's the same watt in here. All of a sudden, or vice versa, I don't have a heat source in here. In other words, the heat that is 1 watt in here, and all of a sudden 2 watts pop up out of nowhere, somewhere in the material. So the same wattage is throughout the entire thing in here. That's the same of heat that is going through the entire material. So heat is the same in here. So H for this is, by the way, it's a part of a cone. Okay, so this is of a radius R. This is the radius R. So it's going to be K times pi R squared divided by the length dx. The length is dx, and the gradient in temperature, this is situated at temperature T plus dt, and this is situated at temperature T. Okay, remember it's hotter always from this side, from the TH. So the gradient in temperature is simply dt. That's the difference in temperature. And it starts gradually from TH and it goes down to TC. Okay. Somewhere in there is a slight difference in temperature, and that is what driving that current to begin with. It's this dt between this region and this region of width dx. One of them is slightly hotter than the other by an amount, differential amount dt. Okay. Makes sense?
Yes.
Okay. Then the whole problem then is trying to find what that R is. That's all. You can clearly see from the geometry in here, R is this shape, and X is this much. If X equals to 0, S is equal to 0, R is equal to big R1. If X is equal to L, R is equal to big R2. That's it. This is R2, this is R1. So all I have to do is find the equation for this line. This gives me X in the X-axis and R in the Y-axis, that's all. So this is a function that passes with these 2 points, 0 R1 and L R2. And whichever method you're going to use, you can find the slope of the function and the y-intercept. The y-intercept is already R1, y, which is in this case R. By the way, this is R now. So R is simply equal to the slope times X plus R1, because this is the y-intercept. And the slope is clearly equal to R2 minus R1, this is the rise, divided by the run, and the run is L. So this is L, and this is R2 minus R1. Case in point, let's check. For X equals to 0, R is equal to R1. For X equals to L, I will have R2 minus R1 plus R1. So that means R is equal to R2. So it makes sense. It's correct. Okay. So the expression then I have in here is H is equal to K times pi times R squared, and R squared now I have an expression for it, which is equal to R2 minus R1 over L times X plus R1 divided by dx times dt. Okay. Move the dt to one side and the dx to the other side, and I know dt changes from th to tc, and I know also dx changes from 0 to l. That's all. So and that's the integration basically of this expression. So this is squared, by the way. So this becomes h is constant. It's constant throughout the whole thing. So this becomes dt equals to h divided by k times pi times R2 minus R1 over X, over L times X plus R1 So just a matter of integrating this integral. Sorry. This is integrated from TH to TC. If we took the other way convention, we're going to integrate from TC to TH. That's all. Okay. Equals to the boundaries of integration from here is from 0 to L of H dx over K times pi times R2 minus R1 over L x plus R1, the whole thing squared. Whichever method you're going to be comfortable with, at this point, you can make a change of variable. Let's call it y equals to R2 minus R1 over L times x plus R1. That means that dy is equal to R2 minus R1 over L dx. And that gives me dx, which is L over R2 minus R1 times dy. And this becomes just y squared. So the integration in here, first of all, on this side is going to be TC minus TH. Is going to be equal to, on the other side, I will have H over K pi, H over K times pi. Pi is a number, so it goes first, times the dx, which becomes dy divided by this number, or times L over R2 minus R1, times the integral at the end of dy over y squared. Now the boundaries of integration will change, okay? Because when x is equal to 0, this whole thing becomes R1. So this is from R1. When x is equal to L, this whole thing becomes R2. That's all, from R2 to R2, okay? So that's the boundaries of it, as if we're integrating over R, that's all. So this is going to be minus 1 over y times this expression. So this is going to be TC minus TH is equal to H with a minus sign coming from this integral, H over pi k times L over R2 minus R1 times the function 1 over y evaluated between R1 and R2. Does everybody follow at this point? This is calculus stuff, okay? Make sense?
Yeah, makes sense.
Okay. So at this point, I will have 1 over R2 minus 1 over R1. And 1 over R2 minus 1 over R1 is going to be a negative value. So it's going to be TC minus TH, which is delta minus delta T, by the way, because this is a TH is hotter than TC. So this is, in order for me to talk about this one being positive, or let's leave it for right now. Okay, let's leave it until we rearrange things. It's minus H over pi k times 1 over R2 minus 1 over R1. In this, the common denominator is R2, R1. And in numerator, I forgot the R2 minus R1. R2 minus R1 in here, which is coming from this term, times L. And this will have an R1 minus R2 in it, okay? Obviously, R1 and R2 with the difference, and you have R2 minus R1, and the negative sign will take care of itself. And at the end, it's going to give me the following expression. They will cancel basically the numerator denominator. It's going to give me TC minus TH is equal to H over pi k. I already took care of the sign, times L over R2 minus R1. Which means, I'm sorry, there is not minus, it's going to be multiplied. That's the common denominator, R2, R1. And the difference is going to be canceling with the negative sign. So at the end, H is going to be equal to pi times K times R2, R1 over L times TC minus TH. Okay. What this is telling me is, you can clearly see from this expression is that H is negative, okay? That means that there is a the first convention is more accurate because of the contradiction in the text. Okay, so this really should have been TC, and this should have been TH, and the whole math would have made sense to me at the end if we stick with the same convention. If we go back to the book, to the original one, namely this is TC and this is TH. Oh no, this is TH and this is TC. Then in this case, I have to be careful in here and assume, since I'm starting with a value T, that this is T and this is T plus DT. Okay. If I do that, everything will be fine, except in here I will have a negative DT, and that negative will cancel this and make this one positive. The bottom line is the following. Heat will always flow from the hot source to the cold source. You cannot have it backward, okay? Because clearly this expression here is giving me a heat that is negative, a heat current that is negative. Okay? Barring this technicality, which is coming from actually the confusion in the verbiage itself, and the only way to solve it is using physics. If one is mathematician, doesn't care about the physics, they will find an answer and they say, okay, here is the answer for you. But you have to have sense to you. And the only way this makes sense, if this was hotter and this was colder, and then the, okay? If you want to have it the way that the verbiage is fine, your mathematics in this step in here to account for you're moving the temperature from point to point. That this is X. Let me go back about the algebra. This is the point X in space, and this is X plus dx, where you took the slice of width dx. Then this is T, and this is T plus dt. Saying that my T is starting from whatever this value was. This was TH, so be it, TH. And this is T cold, so be it T cold. Then, as if you're saying that the heat is transferring from a colder source to a hotter source. But that's a mathematical trick no more. And at the end, you're going to get the correct answer. Okay. I want you to really think about this problem a lot because of the fact that it has some, first of all, contradiction. This is not me saying that. The book itself has a picture and it has verbiage. Okay. And I left it as such because I want you to go through this. The mistake was, and the mistake has to do with the fact that it flow from the have H in this case negative, meaning that the heat is actually flowing in the opposite direction. Okay. To fix that mathematically, you have to go back to the elements of calculus. You start with point X, you define its temperature T, because you're finding T is a function of X. That's all. Okay. So, and this is exactly the situation in this case. That's all. Okay. But this is the answer.
DJ?
Yes.
Quick question. In the back of the book, the final answer for 113 is K pi R1 R2 divided by L. How come pi K isn't divided by L as well?
It's divided by L in here, no? This is L. I don't what is the I mean, you saw probably it says K times pi times R2 R1 divided by L. Is that what you're saying? Times delta T?
No, the pi and K, or K and pi are also divided by L, not just R2 and R1.
Can't be. What is the which
It's in the answers to odd numbered problems, A-14 in the back of the book.
I'm looking at the book.
Wouldn't it be that since it's just multiplication that they can all just be written under the same fraction though?
Yeah, I think it's the same thing. Yeah, I'm looking at it right now. It's the same thing. The division is the same everywhere. Is that what you're saying, Gabriel? The line
Yeah.
has to extend all. That's the
No,
same thing.
I was just curious because on the at towards the end, I wasn't sure if that would make a difference, but I guess that is the
Yeah.
end.
Okay. Yeah, it seems like, and okay, it's a good idea to look at the solutions at the end, but the point in here, you have to be careful with the way that things are. I think it looks like they had a solution that follows the shape, that follows the graph, not the verbiage. Okay, remember that they have a problem in this problem. The author had an issue in here in that the verbiage is different than the picture, but the solution, it looks to me like they have it following the picture, not the verbiage. Okay, but I want you guys to focus on that issue. I'm glad that you brought up this issue in here, but it is the same thing. Okay, it's a good point to remember that this expression R1 times R2 will reduce to the correct answer if in case R1 is equal to R2. Because if it's R1 equal to R2, then it's a cylinder, no more, okay? So if this is R and this is R, so this is a cylinder and this is the cross section, which is pi R squared. So if R1 is equal to R2 is equal to R, what we're looking at is the area pi R squared times K divided by L, which is correct, okay? Times delta T is H, which is the original formula from the book, which is 1721, the one that we discussed in the beginning, okay? Does this problem make sense to you guys?
I mean, kind of.
Okay.
I need to rework on my math.
Okay, no problem. Listen, as I said before, I went in kind of detail about this problem for a reason. First of all, to discuss the confusion in the problem itself. The problem itself has an issue in the fact that it's defining things and drawing things against those definitions. So you follow whichever way you do, but at the end, you have to be in control. You're the one who's the driver. You have to tell it exactly where the problem needs to go, okay? Because you know the physics tells you something in the fact that heat can only go from one direction, not from both, not from the opposite. I mean, if you have a hot cup of coffee and you put it on the table and you come back later on, you're not going to get it any hotter. It's going to be colder, actually. It's going to be room temperature. It's going to be probably something you don't want to drink. Same thing, if you bring a super cold cup of water that you would want to drink and you forget it on the table and you come back later on, you're going to find it something that is not as cold, because heat will always flow in the first case from the hot coffee to the room, and the second case is going to be from the room to the cold cup of coffee. That's the idea behind it in this case in here. So I want you to really always think about these problems. And at the end, we took even the case when the two R's are the same. Namely, I'm dealing with a cylinder. Does this expression make sense? Obviously, if it's a cylinder that we're dealing with, let me go back to sharing the screen. If we're dealing with a cylinder, then we're going to throw in the formula exactly from the get-go. Then H, if it's a cylinder, is going to be K times, there is nothing that changes, times the area divided by L times delta T. And the area is a cross-section of the cylinder. Cross-section is pi R squared. And if it's a cylinder, the two radii will be the same. R1 and R2 will be the same, will be the radius of the cylinder, R. So this R2 times R1 will become just R. That's it. So this expression makes sense because at the end, it resolves back to something we know for the cylinder, okay? So at the end, once you find the solution, try to discuss it and see if it makes sense to you. Sounds good?
Sounds good.
So we're gonna do more examples down the road, probably not from this chapter anymore, but from other chapters. And you will see these techniques applied a lot, namely that you have to read the problem, draw as much graphs as possible from it, come up with kind of geometry relationships like the ones we have in this case, and then also calculus relationships, whatever you have. Take note of facts like, for example, H is constant. H has to be the same. because I'm assuming in here that there is no accumulation of heat at some point in the material, or there is no heat source from the material itself. It's basically simple conducting material. That's all. Takes heat from one side and drops it to the other side. That's it. In raising the temperature of the other side and lowering the temperature of one side. Okay. It's like the wire, for example, of electricity, which has no batteries in it to begin with. If you put a wire between two ends of a battery, all the role of the wire is conduct charges to move them from one point to the other, because there is a difference in potential. In this case, there is a difference in temperature. So the difference in temperature plays the role of difference in potential. That's all. As a matter of fact, you can take that analogy with Gauss's law, with the, I'm sorry, not Gauss's law, with what's his name, Ohm's law, to this extent too, in the sense that delta T plays the role of the voltage, delta V, and the heat current plays the role of I. So in this case, you say that delta T is equal to RH, and in the other case, delta V is equal to Ri. And you take two materials, for example, of different conductivities, different length, different cross sections, as a matter of fact, and you put them one next to one another, and you will see, according to Ohm's law, this resistance R1, this resistance R2, the equivalent resistance, if this is sitting at temperature T1 and this sitting at temperature T2, the heat, which is the same again as it hits this material, is going to go through this material to come out from the other side, which is equivalent to current, is going to obey the law in such a way that this is equivalent to one material of a given heat resistance in such a way that the sum of the two resistances are the same. So this is, and the same thing. If you take two windows, for example, and you put them one next to one another in a room, so this is window 1 and this is window 2, this is escaping a certain amount of heat H1, this is escaping a certain amount of heat H2. The total heat escaping in this case is going to be H1 plus H2. The inside is sitting at the temperature T inside. The outside is sitting at a temperature T outside. So the delta T is the same. So this is equivalent as saying delta V is the same. And the heat, in this case, there is a relationship between the current is I1 is equal to I2. And you can use the parallel circuit basically from what you did in physics too. So namely that in this case, the equivalent resistance, the heat thermal resistance in this case, is such a way that this is the relationship that it obeys. So basically you can find how much heat is going to escape from the room just by adding those two windows together. So a lot of the discussions can go further. I mean, no, I know, listen, we're not doing heat transfer in this class, okay? This is just a small section from a big chapter. We're talking about heat transfer. So this topic, especially if you're gonna be an engineering student going into applications for this field, this is gonna be a big topic by itself down the road, okay? So we're not gonna delve too much in it. So we're going to go straight into our lab. Unless you guys have any questions related to this stuff. No questions? Alex, if you said something, I did not hear it.
No, I think I'm good.
Okay, very good. So let me share the screen for the lab. When you come to the lab, okay, these are the instructions for the lab. Okay, this is what I was saying in the introduction before. If you see a date in here, excuse me, that is different than when this is due, okay, please follow this date, not this one, not in the instructions. Please follow this due date, not this one, okay? This is from a previous instruction, so please ignore this part and just follow this one. Does this make sense?
Yes.
Yes.
It's not always the lecture date. It's always the canvas date. This is the canvas date. This is the instruction date. Okay. So the first thing that you need to do is do this. It's a good idea to have Adobe Reader. okay? If you have the Adobe editor, that's even better. But if you don't have the Adobe editor, it's a good idea to have the Adobe Reader. I mean, this is not as much as a problem as it was in the past, where people use browsers, and browsers are, what do you call them, stateless, in a sense that if you make any changes, the changes do not persist. Nowadays they persist, but it doesn't matter. Get an Adobe Reader so that whatever changes you make to your file are going to stay. This is, as one of you mentioned before, this is a fillable file, meaning that whatever you put in it is going to stick in that file, okay? So this is what you have to do. First of all, put your name in it and come back to it and see if your name has been saved. Put whatever information in there, come back. The worst thing you would want to do is finish your lab report and you think that you're done with everything. You have all of your data, you have all of your graphs, and everything looks immaculate, and then you upload it and nothing was uploaded. The whole file is empty. That's terrible. You are still responsible for this one, in the sense that if for some reason you don't have the Adobe properly working for you, and I know probably sometimes it's an issue, especially for Mac users, you still have to do the lab report. You don't have to do this PDF file at all. You can generate it using your own Word file or alternative method. When you do that, please refer to the items, because when I'm grading your lab, I go in this sequential order. So do not put question 4 here and question 1 way back. So it's going to be confusing and it's going to be unorganized, and it would not be able to find it. So you're going to go in this sequential order if you are choosing not to use the PDF file, using your own version. So in other words, you are required to submit the lab report, whether able to use the PDF file or not. That is not the issue. The responsibility is still yours to submit the report. It's easy actually to do the PDF file if you can. If you can't, then you have to come up with your own solution, okay? At the end, upload your work to Canvas in the form of the file, and preferably in a PDF file still format. That way the file retains its formatting. If not, try to stick to things that are standard. Do not give me something that is Google Docs, for example. Do not try to use them, because sometimes it happens in the past where people give me a Google Doc link, which means I have to have a Gmail account to access their link. And that is terrible, because I don't have actually the file itself, and there is an expiration on it, but for security reasons that Google puts on those things. So don't do that, okay, please. Or even using Office 365 and putting things on Office 365 and thinking that you actually have uploaded a Word file, but you uploaded a link to your own Office 365 account, in which case you have to give me permission actually to access your folder. And that is not good. Just download it to your own local computer and then upload it to Canvas. And then from there, I will have access to it to be able to grade you for your work. Does this make sense?
Yes.
Okay, very good. So I'm counting on you guys to be to at least test this method. I would say 95% of the time it works. If it doesn't work for you, please let me know so that we can find a way to probably communicate with one another. Saying 95, I don't know. I've never done statistics, so it could be 93.2. I don't know. Okay, so don't quote me on it. Okay, the rubric. Almost all of your assignments will have rubrics, so follow them. This is how you're going to be graded for all of your assignments. So in a sense, there is a check mark in here. I can take this rubric and have to wait for an instructor to grade my work. I can actually put a grade for myself if I did everything that this thing is saying I'm supposed to do. Okay, so the rubric is an important part of your lab, so please stick to it and try to follow it as much as possible, because that is how you're going to be graded. So don't miss that opportunity. For this lab, it's kind of easy because we only have that PDF file, which I have already downloaded to my computer. I'm going to switch from
DJ, one quick
From,
question regarding the lab partners. So if we have 3 lab partners, do all of us need to turn
Sorry?
it in separately?
yes, absolutely. Okay, if you are working in teams, which is you're allowed to, you're going to Gabriel, were you saying something?
Yeah, we each have to turn it in separately, right? Or how does that work?
Yes, yes. Everyone will receive a mark for him or herself, okay, independently of the others. So if you are 2 people or 3 people working together, that is great. That is good news, actually. I like that very much. But please submit your lab separately because your grade is going to be separate from the others, okay? So we're clear on that. The only thing I require in here, under name, your name need to go first, and all of the other team members need to be included in the name. That's all. So if I am here working on this, I'm going to put my name. And if Gabriel worked with me, so I'm going to put G. I'm sorry if I say your name wrong, Lambera. And then if I happen to have Cameron also working with us, I can put Cameron in here. But if the names, and I see that there are some names that seem to have the same, so I can go the whole thing explicit, okay? In other words, if there is a confusion, try to avoid it, okay? So for example, Cameron worked with us on this, okay? But now there is no questions about it that we work together on this lab. But you, the first one, is going to be receiving the grade for that lab. Excuse me. The others will not receive a mark unless they submit their labs. Okay, they will get 0 actually if they don't submit it. But okay. Okay, every lab will have an objective in it, and the objective is graded. So you can go and look at exactly how much grades you're going to have. So you can see the grades for the objective. As I was saying before, this formula is wrong. The A should be in the numerator and the L should be in the denominator. Okay. Word of caution for this lab, it's not using the joules, it's using calories. Okay. So it's fine. If you care to convert this table into calories, all you have to do is multiply this number by 4,190, and you get it in joules per kilogram, not per gram, or 4.19, and you convert this whole thing into excuse me, into joules per gram per degree Celsius. Finally, also the conductivity is given by calories per second. We could have used watts, which is joules per second, and centimeter instead of meters and degree Celsius. Okay, excuse me. Iron is a good conductor. Gold is an even good conductor. Copper is actually a very good conductor, and so on and so forth. Those are metals. Those are good conductors of electricity. Nitrogen, which is air really for the main part, is very low. Oxygen, which is air also, is a poor conductor, and so on and so forth. Okay, but it conducts heat nonetheless, provided that there is no motion of air. If there is motion of air, then you have convection, which is another phenomenon. Okay, there are questions in here that I want you to understand, to go through. Look in your home for a steel plate or spoon and a wooden plate or a spoon. So one is made out of steel, one is made out of wood. Leave both sitting in thermal contact with the countertop of the kitchen for quite some time. Are the 2 plates at the same temperature, yes or no? To put the 2 in the place for a long time. So that's what you have to do. You have to do it at home. Okay, take a piece of wood, take a piece of iron, steel, your spoon, or whatever you have in there, and put them on the countertop and wait for it. And then, are they at the same temperature? Yes or no? If they are, now simultaneously put one hand on each plate. So put one hand in here and one hand in the other, and see which one feels colder. Is it going to be the wooden utensil, or is it going to be the metallic utensil? Okay. Obviously, you're going to feel a difference, and you're going to tell me what are you looking at? Are they at different temperatures, and which one feels cooler, and why? Okay. Does this make sense to you guys? What you're supposed to do?
Yes.
Let's answer the first part. The first part of this. If you take a wooden utensil and a steel utensil, and you put them in the room for a long, long time, are they going to be at the same temperature? Yes or no?
No.
No.
Two people spoke. Alex, what did you say?
No, they won't be the same temperature.
Same temperature. Does everybody agree it's going to be the same temperature?
No, it won't be
No.
the same temperature.
Different temperature.
Why?
Thought
I
it
mean,
would
I
be
take
the same temperature, right?
yeah. If you put them for a long, long time in the same room and the same place, the same conditions, they will reach thermal equilibrium with the air in the room, and whatever that temperature in the air is going to be their temperature. Make sense?
Yeah.
Because even if you take one of them from a refrigerator and you take the other one from the stove and you put them on the same countertop, not in contact with another, I mean with one another, just on this countertop, and wait for a long, long time. When I say long, long time, whatever it takes, okay? Because they're in thermal contact with the air in the room where they are, they're going to reach thermal equilibrium with that air, and that air being the same, so they will both be the same temperature. So that answers that part. Okay? Now the second part is the one that you have to understand. You have to find a solution to. Because if you touch them, one of them will probably feel cooler than the other. A wooden utensil and a metallic utensil. One of them will feel cooler to you. And you have to explain to me why is such, if they are the same temperature, of course. If you don't agree that they are the same temperature, then you have to explain to me why. Then place an ice cube. Try to take as much ice cube, I mean, the same amount of ice cube, okay? On each plate, spoon preferably, okay? Or spoon, plate or spoon, doesn't matter. Try to stick with the similar geometries, okay? On which plate does the ice cube melt faster? The wooden utensil or the wooden plate or the wooden spoon or the metallic one, the steel one? Which one the ice, I mean, you're gonna notice. Wait for a few minutes, and you're gonna notice one of them will melt faster than the other one. Again, you're going to try to explain that to me. They're both at the same temperature. So what's going on? There is something else going on in here. Make sense? Now, if you have difficulty with these questions, please let me know. Okay, this is not supposed to be a challenge where you cannot, if you cannot find the answer, you're gonna have a problem with it. No, please let me know. I'll be more than happy to discuss it with you. And if you agree with me, you're gonna put the answer in there. If you don't agree with me, that put your answer, the one that is you're convinced of. Okay. Question 3. Suppose you are going to defrost some hamburger meat. This is related to these two questions. For dinner tonight, would you be better off defrosting it, wrapped of course, by laying it on a wood cutting board or on a metallic dish? Which one would be better? This is related immediately to the question before, okay? After you see which one melts the ice faster, then you probably would want the one that melts the ice faster, because that's exactly what this process of defrosting is, okay? Question 4. Define the following: internal energy, heat, and temperature. I would recommend reading through the questions before these questions in here. And there is no wrong answer to this one at this point, because we did not define the internal energy yet when we talked about it in class. heat is a transfer of energy in the form of difference in temperature, and the temperature we defined it already. Okay, but we still don't have quantitative experience. You need to read the lab to be able to answer this question. As I was saying, even if you get it completely wrong in here, I'm going to try to be as lenient as possible, but I would like you to read as much as possible and get it correct. Okay, so read the question, the stuff before, because the explanations are before. Okay, so it's temperature, heat, and internal energy. Okay, which is hotter, a red hot nail or a bathtub filled with ice water, which has more internal energy? This is related to the question before. Once you have the definitions correct from reading the previous stuff, and once you know about Q equal to MC delta T, you should be able to answer this question. Okay. Again, if you're struggling with it, please let me know. I'll be more than happy to discuss it with you. This is the stuff that we were talking about here. So you have a solid that goes through a temperature change from T hot to T of equilibrium. Okay. You have its specific heat CS and you have its mass MS. Okay. You have the water, which goes from its T cold to the T of equilibrium, TW in this case in here. Okay. And you put them together. This is similar to exactly what I was saying. So basically what you have in here, you have a solid, hot solid, and you have water, and you bring that and you put it in here. The temperature of the solid will go from TH to TW. The temperature of the water go from T cold to TW, the equilibrium temperature, okay? And from here, you're going to find the expression for both of them. Granted, in this expression, seawater is known value from the table, and the MS, the mass of the solid, is determined from the lab experiment, and the TW and the TH and everything else is measured and given. And from here, you're going to find the C for the solid, okay? You have aluminum, copper, iron, what is this? Silver and strontium as elements that you're going to be experimenting with, and you're going to find the different values for CS. For this lab, where is the link for the lab? Here is the link for it, okay? I'm going to copy the link. I'm going to open it using a browser. So let me stop sharing that screen and let me share with you this screen. So this is the experiment that you guys are going to be conducting in here. So I'm going to click on the experiment. So let's run the experiment for right now. Okay. We're going to start with a solid. Okay. Choose a solid. So let's take, oh, that was 10. I'm sorry, SN. So let's take, I don't know what they ask us to do. If I go back into the table and the instructions, the first element and the mass of the aluminum, did they tell us how much I should put of mass? So they said choose enough large mass in here. So I'm going to choose, let's say, for example, 37 grams is fine. We're going to choose a temperature. Let's say, for example, it's 150 degrees Celsius. Okay. And then the liquid is going to be water. So why is this not running for me? Is it because I'm running, okay, for some reason, this link is not working well for this page in here. So let me see if I can get a different browser. which means that probably some browsers work better than other browsers. Aluminum. Yeah, you see, immediately from the get-go, when I used it in Firefox, it gave me the animation quite quickly. So do you guys look at the animation now? Do you see it? So I took
Yeah.
aluminum. So I'm going to take a mass, and I even have the drag and drop points in here. So I said 37. Let's stick with this. 38 is fine. The temperature 160, that's fine. It's giving it even the temperature in here. The liquid. Why it's not showing me the okay. Are we supposed to start with the water first? Okay, the water. Okay, the temperature. Stick with room temperature.
Click the next on the bottom left, maybe? I don't know.
Absolutely, you're right. Okay, so thank you very much. I did not even read the instructions, then it's in the instructions, you're right. So let's go back into the audits again. Yeah, thank you very much for pointing that out. Okay, so 37. Next, you're right. Okay, so the liquids is going to be water. That's the only choice you have. And the temperature is sitting at 20, so you cannot change the temperature. And the mass you have in there. So the next that you're going to do in here, try to take a big enough mass. Not too big though, because the instructions tell you not to take too much big in there. So let's do this next. And let's start, okay? Show the graph for view. It's going to give me the temperature of both the aluminum and the H2O. And start, okay? So we're going to take that basically aluminum and put it in there and close on it and watch the temperature of both substances. Because I didn't take a lot of water. See, because of the specific heat of the water, it's not going to, temperature does not change that much. It was 20 degrees. The other one was 160 degrees. Okay. And then at the end, it's going to reach a thermal temperature. This is TW, by the way. Okay, 29.89. Okay. I'm going to put that in the table, okay? So don't forget to click that next thing, otherwise you're not going to be able to complete the simulation thing. So let me go back into stop sharing and let me share the PDF file. So you have the mass of the solid, the mass of the water, and the temperature of the solid. The temperature of the water is given for you. It's always going to be 20 degrees. So that's not going to be changing. You're going to change from aluminum to copper to iron to silver to tin. Okay. And you're going to record the equilibrium temperature in this case and the temperature of the solid. Those are the things you are going to change, and the mass of the water. Okay. Please follow the instructions. And in here, when visit the experiment, tab the experiment. From the mass, choose the mass of the aluminum. From the mass slider, choose the mass. And then from, you don't need to check on the status, okay? So you don't need to see the specific heat, and click next. That's what I missed earlier, okay? You have to click next, okay? In the left pane in order to continue. So at the end, once you follow through all of these steps, know the temperature is fixed at 20 degrees. So then you go back into this formula and you find CS of that solid, okay? The CS of the solid is going to be the mass of the water that you're going to determine divided by the mass of the solid that you're going to determine. T equilibrium is going to be given to you. That is the temperature, 28.98 or whatever that temperature was in our case. And TH was 160 degrees that we chose. This is 28.9. So it's going to be a value for that solid in calories per gram per degree Celsius, okay? And once you have that, you're going to measure the values of C and you're going to plug them in here. You're going to compare them to the typical values and you're going to find the errors in percentage in here. given that the water has a relatively high acidity, why will using too much water give you a poor result? Okay, you need to think about that, because if you put too much water, not all of the water is going to basically interact with the environment behind it, especially the container and also the air, and lose that heat in there. So you really don't want to use too much water. You would want to use as much as you need only. This, if we did this in the lab, we'll have more errors than this one's in here, okay? And again, if you find too much errors in here, please blame it on the simulation itself, okay? When comparing the heat specific of most materials, such as rock, to that of water, how does this? The specific heat of water will always be high enough, and this explains what's going on in the weather, okay? In the between the hot deserts and the cold areas. And this is the conclusion to the lab, okay? So, does the lab make sense to you guys?
Yeah, pretty much to me.
Yeah.
Very good.
I think so.
So what I'm going to do now is actually a lab session. I know we chewed from it and we did even some stuff from the lecture stuff. You could wait now, or you could leave and work on it later on. I'm going to leave the computer open for you guys if you have any questions. And if you choose to do it later, that's fine too. And I'll see you Tuesday next week.
DJ, I had one
Another-
question regarding the labs again.
Uh-huh.
So if all three of us, so I have two other lab partners that are down to work on it in here already. If all three of us work on it together, we can just do one PDF and then just redo the names. That's okay.
That's fine, as long as I see the names different, that's all, okay?
Okay, perfect. Thank you.
Here's the deal though, if you don't agree with what they're saying, you might need to put it in your own words, okay? Because sometimes people don't agree on something, okay? And because they might be losing points where you would want to gain where you think you're right. So you might might be different than they are. In other words, consensus is not always the case.
Fair enough.
Okay. So I'm gonna leave the computer open. If you guys have any questions, just ask and give me a minute or two to reach you in here. Okay, half a minute or so. Okay.
Thanks, Professor.
Problem. Thank you, Cindy. If you choose to leave, that's fine too. Okay.
Thank you, Professor. Have a good day.